Hey guys, so I thought I would do a quick overview on if you've ever wondered, if you're a chemical engineer, what the residence time is for a particular desired conversion and flow rate and volume of a reactor. How are all these terms related to each other? And so it can seem daunting, and hopefully this video will clear things up for some of you. And yeah, so if you're interested in this stuff, great, and hopefully this makes sense. So we have three main types of chemical reactors in industry. We have the CSTR, continuous stirred tank reactor. We have something called the plug flow reactor, or PFR, and then we have another thing called the batch stirred tank reactor. And they're all slightly different, and they all have different applications in industry. So the CSTR is involved in primarily liquids, and what it is you've got this reaction vessel, you've got some kind of propeller or series of propellers that spin rapidly inside, and it creates a homogeneous solution inside the tank. The continuous part, the C part, means that you have flow in and out of the system, and consequently it's used for creating large quantities of stuff. So sewage plants that have to process a bunch of waste are a great example. You've got a massive volume of material you have to work with, and it's all in essentially an aqueous form or any kind of solution. As long as it's an incompressible fluid, that is the key point, and that's when CSTRs work best. And so starting out with a mole balance on a generic CSTR, we can assume that it's operating at steady state, which means that any time derivative of any term, whether it's the number of moles in the reactor or the concentration in the reactor or the pressure or the temperature, it's not time dependent. It's constant with time. You can still have a concentration gradient within that reactor, although because it's stirred, you do not in this example, but any d by dt term is equal to 0. You can have spatial variation though, but not in stirred tank reactors, so it is a little bit confusing, and I apologize for bringing that up. But starting with a mole balance, you have dNA dt, that refers to the number of moles of species A. So how is the number of moles of species A changing with respect to time? You've got FA naught, which refers to your inlet flow, molar flow rate of A. You've got FA, which refers to the outer molar flow rate of A, and you have this generation term of A because we're working with moles, not mass. So we can have moles of A disappearing if you have some kind of reaction occurring, and you will have to take that into account. You can also have moles of A appearing if it's being generated. You take that into account through this integral here. And so if something's operating at steady state, as we just said, we can cancel that term. If it's an incompressible fluid, it makes things nice for us because FA and FA naught are referring, as long as the volumetric flow rate is constant, by definition it must be if it's if you're at steady state and it's an incompressible fluid. It lets us make simplifications within these terms that makes life easier later on. And because it's a stirred tank reactor and it's homogeneous, we assume constant temperature, pressure, and a concentration vector. Concentration vector refers only to if you have multiple species present, like the concentration of A, B, C, D, whatever. Don't let that interfere too much with this, but as long as all of those are consistent and homogeneous throughout the reactor, your reaction rate will have no spatial dependence, and consequently you can pull it out of your volume integral here, which makes life nice, and we end up finding this relationship between volume and rate of reaction and molar flow rates. And so what we end up finding ultimately, and this is the theme here, is that your residence time, which is the amount of time a molecule must spend in a reactor, is dependent on the rate of reaction and how much you need to convert. So it's a war going on here. Rate of reaction is R, and X is referring to your rate of conversion. Rate of conversion is a number that varies between 0 and 1. So 1 is 100% of conversion, so 100% of the moles of A that you put into the reactor actually got converted into your product that you wanted, and then you've got any number in between. And because our volumetric flow rate is constant, it allows us to, instead of having to do, it allows us to make this relationship saying that your inlet concentration minus your outlet concentration. So this is the number of moles of A that were actually converted divided by the number of moles of A you fed into the reactor. So it's essentially an efficiency term, is equal to this relationship, and you can simplify it accordingly to find that X times FA naught, so your desired conversion times your inlet flow rate, is equal to the difference between the inlet and the outlet molar flow rates. We can take this term here and we can notice that it appears in your volume term right here. And consequently, you can substitute in X times FA naught for this term here to get your volume of your reactor as a function of your desired concentration, desired conversion times your inlet molar flow rate divided by your rate of reaction. And to then solve for your residence time, if you divide the volume by the volumetric flow rate, V naught, what you realize is if you do a dimensional analysis, you have cubic meters divided by cubic meters per second in the denominator. Seconds comes up to the top. You have a unit, tau, which is referred to as residence time, that has units of seconds, which is what we want. And so because of that, we can now define tau, the residence time of a continuous stirred tank reactor, to be X times Ca naught divided by minus Ra. We have this minus sign here because we assume that A is being produced. So if Ra is a positive quantity, it means that you have moles of A being produced, but we have A being reacted in this case, so the moles are disappearing. So we need this negative sign here to ensure that our residence time is a positive value. And this is how you derive what your residence time should be for a continuous stirred tank reactor. Moving on to plug flow reactors, there's a relationship you can look up in your textbook that tells you that the rate and change of the molar flow rate with respect to volume is equal to the rate of reaction of A. And we can again use this relationship from earlier about our rate of conversion being equal to the amount of A converted divided by the amount of A fed, and performing some more algebra that you can follow through on your own time, we end up finding this relationship that your rate of reaction of A is equal to minus FA naught, your inlet concentration, divided by dx dV. We can further integrate this example, plug in some values, and you can follow through the math here on your own. Just pause the video. What we end up finding is that your volume divided by your volumetric flow rate, which is your residence time, is equal to the integral of Ca from Ca naught to Ca of dCa over minus Ra. And this is our governing equation for the residence time of a plug flow reactor. And then we have batch stirred tank reactors, BSTRs. The difference between plug flow and CSTRs is that both PFR and CSTR have flow in and out. They're used for large quantities or volumes of gases or liquids. Batch stirred tank reactors, you close the lid, you walk away, you come back, and you get the product out after a certain amount of time. And so what we can do is we can calculate, if I wanted to achieve X conversion so like 99% conversion in a BSTR, how long would I have to wait? And so we again perform a generic mole balance on a BSTR. We have no inlet and outlet, so we can cancel these terms. We find that dNA dt is equal to RAV. Moving on, we can substitute in our initial and final conditions in this example. And the problem that I was working on, we were dealing with trying to find what time would be required for a 99% conversion, but we can leave things generically and keep things in terms of x, so any conversion you want. You get time is equal to the integral from 1 minus x CA naught to CA naught dCA over minus RA. And so this is a summary of the relationships we discovered, and the next step here is if you wanted to find how long you would have to wait in practice given a rate of reaction, what is the best kind of reactor to use? And so this was interesting, and I learned something new going through my homework, was that you have dependence on the reaction order. So depending on what kind of chemical reaction you're working with, you may want to go with a different kind of reactor because they're not all the same. If you have a 0th order reaction in which your reaction rate is merely K, does not depend on any concentration values, what we end up finding is that all 3 reactor types perform exactly the same. So if you're in industry and you know you're working on if you're told to run a reaction that's 0th order, your job of just go with the cheapest option they have, basically, which may very well be batch-stirred tank reactors. But again, there's many other variables to take into account, but they all behave exactly the same, so just go with the cheapest option. What gets interesting, though, is when we look at reactions that are in the 1st order and 2nd order, so higher order reactions, we begin to see that these 3 reactor types we've just discussed start behaving a little bit differently. The continuous stirred tank reactor, when we plug in our reaction rate minus RA into the equation here, we find that we get a residence time to get a 99% conversion, assuming a 1st order reaction, of 9.9 times 10 to the 5th seconds. So that's almost 1,000,000 seconds you would have to wait before you get 99% conversion of your inlet feed. Contrast this with a plug flow reactor in which we integrate over each point in the plug flow reactor. I might make a second demo of what a plug flow reactor is because it's a lot of information for this, but because you're integrating, a plug flow reactor is essentially an infinitely many number of batch reactors in series right next to each other, and you have these differential elements. What we find is that the residence time of that is significantly quicker than a CSTR. So in industry, if you know you're working with a 1st or 2nd order reaction and you have a choice between using a CSTR or a PFR, in this example at least, and you want to maximize the amount of product you can make, you want to minimize your residence time because the less time product has to spend in your reactor, you can get it out and sell it. Plug flow reactors look very nice. And something else interesting we find is that there's a relationship between PFRs and BSTRs. The plug flow reactors and the batch stirred tank reactors, they have an equivalent residence time. And so intuitively, the reason for that is because you can think of plug flow reactors, as I said, as an infinite series of batch stirred tank reactors. If you take a differential element, a slice of the cross-sectional area of a tube, and look at that over time, it is essentially, because we have no mixing in the axial directions but perfect mixing in the radial directions, it's a batch stirred tank reactor in the form of like a tiny disk or something. And because of that, the residence times are identical, which is interesting, and hopefully this helps you with your chemical engineering homework, or in case you're just interested in what chemical engineers do in industry and what kind of reactor types you have to work with, this is useful to you. Thanks for watching.